Welcome to the Royal Society. I'm Alex Halliday. I'm the Physical Sciences Secretary for the Royal Society. It gives me a huge pleasure to introduce Andrea Ghez this evening. It's going to be a fantastic talk. The place is packed, and we're delighted that she's been able to make it here. Just so that you know, this lecture is being filmed, and it's being supported by a BSL interpreter and live subtitling as well. So if you don't want to appear on camera when you ask the questions, then you might want to ask the questions afterwards over drinks. Let me say a little bit about the Bakerian Medal and Lecture. This is delivered annually at the Royal Society of London. Is accompanied by a medal and a gift of £10,000. It is the Royal Society's premier award for the physical sciences. The lectureship was established through a bequest by Henry Baker, FRS, of £100. The lecture series began in 1775. It's supposed to be an oration or discourse on such part of natural history or experimental philosophy at such time and in such manner as the President and Council of the Society for the time being shall please to order and appoint. So that's what's happening tonight. Winners in the past have included some pretty amazing physical scientists, including Joe Silk, some famous astronomers, Richard Ellis, John Pendry, who's here, Martin Rees, and further back in time, Fred Hoyle, Dorothy Hodgkin talking about insulin, Paul Dirac on the physical reality of quantum mechanics, James Chadwick on the neutron, William Bragg on X-rays, Francis William Aston on mass spectrometry, and Arthur Eddington on interstellar space. Ernest Rutherford gave the lecture twice, in 1904 for talking about, of course, radioactivity, and then later in 1920 he talked about the discovery of the nucleus of the atom. In fact, if you go back further in time, there are a few people who actually gave the lecture several times. I found out that Humphrey Davy gave the lecture 6 times from 1806 every year till 1811, and then once more, but this time on electrochemistry in 1826. I thought this sounds a bit suspicious. He must have been the president himself and actually chose himself every time as the Bakerian Lecture. But it turns out he was actually the president after this period of time. So anyway, if you give a good lecture, you might be invited back next year. So you will notice that all of these people are British Commonwealth citizens. Last year, the Royal Society decided for the first time that the 3 premier awards of the Royal Society, the Copley Medal, the Bakerian, and the Croonian, should be opened up to the top individuals globally. And for those who want to look at them, the portraits are outside on the wall. We've got pictures of these this year's awardees. This brings me to Professor Andrea Ghez, who is Professor of Physics and Astronomy, and Lauren B. Lightman and Arthur E. Levine Chair in Astrophysics at UCLA. I should just like to say in passing that it gives us great pleasure to also welcome Arthur and Zachary Levine, who are attending this evening's talk, so looking forward to talking to them later. Today, Ghez is one of the world's leading experts in observational astrophysics, and she heads UCLA's Galactic Center group. She started off wanting to be a ballet dancer, then she wanted to be an astronaut, then a mathematician. She studied eventually physics at MIT before doing a PhD with Gary Neugebauer, who worked in infrared astronomy at Caltech. After a postdoc in astronomy at the University of Arizona, she moved to UCLA in 1994, and she's been there ever since as a faculty member. Ghez is best known for her groundbreaking work, which has led to the best evidence to date for the existence of a supermassive black hole at the center of our galaxy. She has received numerous honors and awards, including the Crawford Prize in Astronomy. She is the first ever woman to receive a Crawford Prize in any field. She has received a MacArthur Fellowship, election of the National Academy of Sciences in America, the American Academy of Arts and Sciences, and the American Philosophical Society. Gez's work has been made possible through major advances in high-resolution imaging, the technology for which includes, in particular, adaptive optics. Her group continues to work on pushing forwards the frontiers of these technologies. She serves on several committees that provide leadership and support for the WM Keck Observatory in particular, which hosts the largest telescopes in the world, and the future 30-meter telescope. Professor Ghez is also very committed to the communication of science to the general public and to inspiring young women into science. Her work can be found in many public outlets, including NOVA's Monster of the Milky Way, Discoveries Swallowed by a Black Hole, and her TED Talk, which as of today, as I checked this morning, has had around 700,000 views. Today she is going to give us some even bigger numbers than 700,000, and that she is going to be talking to us about the monster at the heart of our galaxy. And will you please welcome Andrea Ghez. You need to stay somewhere near the lectern.
Thank you. It gives me tremendous pleasure to be here, in particular to be speaking at the Royal Society, because so much of this work actually was inspired by questions that were posed by Donald Lyndon Bell and Sir Martin Rees roughly 40 years ago. So it seems very nice to give tribute to them. So let me start with a question. How do you observe something you can't see? Now, this is an essential question if you want to find and study black holes, because these objects have such strong gravity that nothing can escape them, not even light. The story I'd like to tell you today is how we've been able to find a supermassive black hole at the center of our galaxy. And this has not only provided us with the best evidence to date that these exotic objects exist, but has provided us with a wonderful opportunity to study the fundamental physics of how black holes warp space-time and what roles black holes play in the formation and evolution of galaxies. So to begin with, we all have to agree on what a black hole is, and hence the blank side. So while black holes require relatively exotic physics to properly describe them, the way I would like you to think of a black hole today is an object whose mass is confined to zero volume. So despite the fact that I'm going to be talking about supermassive objects, they have no finite size. So this means if we think about density, which is mass divided by volume, density goes to infinity. And in physics, anytime we have a quantity going to infinity, this means we have a giant red arrow that says your physics, description of physics is not quite right. And in fact, black holes represent the idea that we don't know how to make the study of general relativity, which is what Einstein is so famous for, and the study of quantum mechanics, which is the study of things that are very small, work together. So that's the conundrum of a black hole. But despite the fact that black holes have no finite size, there is an important size that we can associate with every black hole. And this size is known as the Schwarzschild Radius, or the event horizon, which was popularized by Star Trek. And this size is important because if you can find or figure out how to compress an object down to its Schwarzschild radius, it will become a black hole. In other words, at that moment, the force of gravity is so strong that it will overcome all other known forces, and the object will be forced to become the infinitesimally small object. Okay, now, so that means that there's two quantities that we need to keep track of, which is we need a mass and we need a size. So how do we figure out how big this Schwarzschild radius is? Now, let's take the Earth. If we could take the Earth and squeeze it down to the size of a sugar cube, it would be forced to become a black hole. Now, the Schwarzschild radius depends simply on mass. So the more mass of the object, the larger the Schwarzschild radius. So if I could take the sun, which is a much more massive object, and squeeze it down to the size of a university campus, and of course I had to put UCLA in there because that's where I'm from, it would become a black hole. All right, so now we have the notion of what defines a black hole. So keep track of this notion, because if I want to show that there's a black hole, I need to show that there's some mass confined to within roughly its Schwarzschild radius. That's the ultimate goal. But before we do that, let's turn to think about where do black holes appear, or where did we understand that black holes might appear. And I'm going to touch on two types of black holes. One is what I'm going to call the ordinary black holes, if there could be such a thing as an ordinary black hole. And then we're going to move on to the supermassive black holes. Now, the ordinary black holes were the ones that were thought of or identified first from a theoretical perspective. In other words, people who thought about the ultimate fate of very massive stars, we realized that those massive stars would end their lives as black holes. So in fact, the star would, the outer layers would explode off. So these are supernova. We see the supernova remnant here. But the inner parts of the star would collapse to become an ordinary mass black hole. So in our galaxy, the most massive stars are about 100 times the mass of the sun. So the top part, those that are 30 times the mass of the sun to 100 times the mass of the sun, would become black holes that are roughly 10 times the mass of the sun. So those are ordinary mass black holes, thought of from theory initially, and then demonstrated observationally. Now, supermassive black holes, the story was very different. And we think that supermassive black holes reside at the center of galaxies. Now, this picture, the scale is very different. So instead of looking at an individual star, we're looking at a picture from Hubble Space Telescope, which shows a variety of galaxies. In the top left, you might notice a spiral galaxy. And that single galaxy has roughly 100 billion stars. So the scale is very different. And the light that we see from these galaxies, this is light that your eye responds to, so the optical, comes mostly from the light from stars. So why did we think that galaxies might host supermassive black holes? And these are black holes that are 1 million to 1 billion times the mass of the sun. Well, the original thinking of about supermassive black holes came from a subset of galaxies known as active galactic nuclei, or AGN for short, simply because their nuclei, or centers, were very active. So this is a picture that's at radio wavelengths. And we see emanating out from the center these enormous jets powering out from the center of the galaxy. And we can measure how fast these jets are moving. And so you can tell that whatever is driving it has got a lot of power. And in fact, at the heart of the galaxy, so that little red dot in the middle, actually has light that's very different than light that comes from stars. So in response to the observations, so note here, the beginning is observations, it was suggested that perhaps supermassive black holes were the engine that drove this really unusual activity in these galaxies. And these galaxies are only 10% of the galaxy world. I mean, in some sense, these are the prima donnas of the galaxies. They're kind of show-offs. And what we see at the heart of the galaxy, because remember, black holes themselves don't emit light. So what are we actually seeing? What we're seeing is that the black hole is feasting on the matter that surrounds it. So they're having an enormous dinner. Right? I'm from the US, so I'd say Thanksgiving. And that's the light that you're seeing, the light that's falling in through the Schwarzschild radius, not the light from the black hole itself. Okay, so now this is what gave rise to the question roughly 40 years ago that Donald Lyndon Bell and Martin Rees asked. They asked, well, is it possible that all galaxies harbor supermassive black holes, and that in ordinary galaxies, these are cases where the black hole is simply on a diet? They're like stealth black holes because there's nothing surrounding them for it to dine on. And so this is a close-up view of that spiral galaxy in the last picture. And this is actually what our galaxy would look like if we could get outside and look back. So our galaxy is a flattened disk-like structure that has spiral arms, and our sun is roughly halfway out. Now, if we were to look at this from Earth, so this is a picture that was taken from the desert of Arizona looking up, what we see or what we perceive of our galaxy looking up in the night sky, because we live in the galaxy, is the Milky Way. In other words, that wonderful trail of stars that cuts the night sky if you can get out to a dark spot and look up. Now, what you'll notice about this is that not only do we see a lot of stars, but we see a dark lane passing through that starlight, and that's the dust in our galaxy. I'm from Los Angeles, so I have a fine appreciation of dust. The dust in our galaxy is just like smog. I guess London also has those smoggy days. So the dust particles are roughly the size of the wavelength of light at optical wavelengths. So it's very effectively blocking the light. But if you go just longward of the optical into the infrared, which is where your TV remote control works or where night vision goggles work, that light penetrates through the dust. So what we would like to do, or what we set out to do, is to ask, can we prove that our galaxy hosts a supermassive black hole? Because, of course, it's the closest example of the center of a galaxy that we'll ever have to study. The next closest center of a galaxy is 100 times further away. So if we want to ask this question of do ordinary garden variety galaxies have supermassive black holes, our galaxy is certainly the best place to address that question. And it also offers the opportunity to introduce the best evidence for the existence of supermassive black holes. Okay, so how are we going to do this? We are going to do this by looking as close as possible to the center of the galaxy for stars. Stars orbit the center of the galaxy due to the gravitational pull of whatever is at the center, for the same reason that planets orbit the sun. So planets, if we measure the orbit, in other words, the period and the size of the orbit, we get to figure out the mass that's inside it. It's a very simple relationship. It's just due to the laws of gravity. So if I want to show that there's a black hole, my job is to show that there is a lot of mass inside a very small volume. So I am inward bound. I want to get to the stars that are as close to the center of the galaxy as possible, which tells you why my dream job was a job at UCLA, because UC owns, with Caltech, the largest telescopes in the world. These are the Keck Telescopes. They're located on the summit of Mauna Kea, which is in Hawaii, which is not a bad place to have to go to work. And the size of each of these two telescopes is described by the size of the primary mirror. So each one is 10 meters in diameter, and that's like the width of a tennis court. This was supported through the Keck Foundation, and when they were built 20 years ago, this was an investment of roughly $180 million. Now, the campaign promise of large telescopes is twofold. There's two reasons astronomers like big telescopes. One is that big telescopes are like big light buckets. You can collect a lot of light that's falling down. The bigger your bucket or the opening, the more light you can collect. So that allows astronomers to see things that are very faint, and in astronomy, things that are faint tend to be very far away. And because of the finite speed of light, this is also a history lesson. So there's a whole slew of astronomers who like big telescopes because it teaches us about the origin of the universe and how the first galaxies were formed. But there's a second reason that telescopes are, there's a second campaign promise of large telescopes. And that is that the larger your telescope is in diameter, the finer the detail that you should be able to see. So this is, I like to make a couple of different analogies here. It would be like looking at an artwork that's made with pointillism. So the closer you are to the painting, you can see the individual dots. So that's the ability to see fine details, to actually resolve out the fine scale structure. The larger your telescope, in principle, the finer your ability to see that detail. So that's the piece I care about quite passionately. Now, it turns out that when I was first hired, people hadn't been able to use the telescope in that mode. And the reason that it hadn't been used in that mode is because of the Earth's atmosphere. So the Earth's atmosphere is wonderful. It allows us to survive here on Earth, but it is a total headache for astronomers. And if you think about it, this is actually some of the data that we took on the center of the galaxy when we first started this experiment. And if there were no atmosphere, what we would see is 5 bright stars, and the size, the smallest structures there that are dancing around would be the size of each star, and they would be rock solid. There would be no dancing around. But the reason that things are dancing around, and this is actually rather amazing, if we think about the light from the center of the galaxy, it's been traveling to us for 26,000 years. And in the last 30 microseconds, it hits the top of the atmosphere, and it goes splat. So they say accidents happen close to home, and that's true in this case, too. So astronomers have been working for many years on a lot of different solutions to this problem. It's a very profound problem. And it is one of the motivations for Hubble Space Telescope. So Hubble Space Telescope is a brilliant solution. You put a telescope above the atmosphere, absolutely no problem. Okay. Now, Hubble Space Telescope, it turns out, compared to Keck, is a relatively modest telescope. The diameter of that telescope is 2.4 meters in diameter, and Keck is 10 meters. So that's a difference. And you might ask, well, how do I think about that difference? And it depends on the kinds of science that you do. But for the kind of science that I do, it goes as the diameter of your telescope to the 4th power. So that's 4 times 4 times 4 times 4. That's, more than a factor of 100. Now think about, in your life, if you had something that you could multiply or by a factor of 100, you'd probably work quite hard for it. And of course, that's what the astronomers have done to figure out, or that's what we've been working quite hard on, I should say. So this is a picture that shows the current, actually it's a little bit old, it's about 10 years old. And the way that you can beat the atmosphere has evolved radically over the 20 years that we've been doing this work. So I want to give you a little bit of an insight into that, but this gives you a sense of scale. So the 5 bright stars that we were looking at in those short exposures, those were about 1/10 of a second. If you take a long exposure, it's going to look blurry, which is what we see. And if you can figure out how to beat the atmosphere, well, you can see a lot more. And in particular, where we think the black hole is, which is in that box, without that technology, you see one big blob. You don't see the individual stars. And with this technology, all of a sudden, you see the stars. And those are the stars that are going to tell us what's at the heart of our galaxy. I'd like to just give you a sense of the revolution that we have been benefiting from in terms of the technology, because I have to say this whole project is completely driven by technology, what you can do today, and it has changed quite a lot. So in the early days, we used a technique that's called Speckle Imaging, and I like to call this poor man's adaptive optics. It was cheap. You could do it. In other words, an assistant professor could actually get it done. But it was kind of limited in what it could do. And nonetheless, it allowed us to get going. So on the left, you see the animation that the stream of data that was taken every year. And on the right, where we're only going to zoom in to the center, where we think the black hole is, shows the result of how we analyzed the data in the early days. So this was basically a lot of computer work to figure out what the atmosphere was doing versus what was actually there. So on the right, we're going to look at a picture from every year. And this is not PR. This is actually the quality of data that we got. And I'd like to show it because it really gives you the sense of progress and what we were able to see. So it's just morphing one year to the next. You can probably identify my favorite star in the universe. There is definitely something moving around quite fast. And at this point, I like to tell the younger people in the audience a little story, because in fact, we started this project in 1995, but in fact, we could have started in 1994. In 1994, we wrote our first telescope proposal to what's known as the Time Allocation Committee. This is an august group of people that decide who gets that precious telescope time. They meet every 6 months. And when we put in our first proposal, they said, 1, your technique won't work, and 2, even if it does, you won't see anything. And at this point, I think my colleagues and I felt like saying, well, why don't you go back and take freshman physics? Because if it works, you're going to see something. And you don't have to work very hard. You don't have to have a computer tell you that there are stars that are moving very fast. Now, since that time, we've gotten much more ambitious about the kinds of ways we can correct for the atmosphere. And that has been aided tremendously by the fact that there are other people in the world who want to look both up and down through the atmosphere. So the astronomers have long been on the hunt for this technique of adaptive optics, which in real time corrects for the Earth's atmospheric blurring. But the military, of course, also cares about this. And of course, they have way more money than the astronomers did. So in the early 90s, they declassified this technology. So there was a huge jump forward due to that. That allowed us to do a much better job than the early approach of speckle imaging. And this is a little animation that shows you how this technology works. There are a couple of miracles that happen, like the dome disappears. It doesn't actually happen. And we're going to see the light from stars coming in. It comes in as a cylinder, and it bounces off the primary mirror that we've been describing, a secondary, and then goes into an instrument bay. It's really, you want to put your instruments in a place that is easy to access. In a minute, we're going to look into the instrument bay to see what happens. So the walls are going to disappear. And we're going to once again see this depiction of light as a cylinder going through the system. There's one very important element in this system, and it's about to bounce off there. That's what's known as a deformable mirror. The job of the deformable mirror is to undo the effects of the Earth's atmosphere. So the Earth's atmosphere has distorted our view. You can think of it as a circus funhouse mirror. And the reason that's going to be helpful to think about is that if there were no atmosphere, we could describe the light as pancakes. So if there's no atmosphere, they should be flat, perfectly flat. But because of the atmosphere, they look like Pringles potato chips. And the job of the deformable mirror is to have the exact opposite shape that the atmosphere has imposed. And of course, that shape is changing on very, very short timescales. So there's some sort of feedback loop that has to happen to tell that mirror how to update. But once it does, it makes that bug splat pattern look clean. Okay, so that's the new modern way, which is so much better than what we had before. And the key to this technology is actually not only the deformable mirror, but whatever allows you to figure out how to reshape that deformable mirror. So today we use lasers that create an artificial star in a layer that's up at 90 kilometers. It turns out the meteorites come down, they deposit sodium atoms, and you can shine the lasers to stimulate those atoms to shine. And that's what allows us to correct the atmosphere today. And I just want to give you a sense of how much better it is today. So on the left, we have what we had before. And of course, that's in black and white. And I like to think about this, I actually really fondly think of this as like the home videos that you had of you when you were a child. They were the best technology that we had at the time, but they're completely antiquated when we look back. And on the right, we have something that's much better. So of course, we have to show it in color. And almost any way we can describe this image on the right, it's about a factor of 10 times better. It's a 10 times sharper, it's 10 times deeper. And in addition to that, for the first time in my professional life, I was taking a picture that was longer than 1/10 of a second, which allowed us not only to take images, which we love to show, but we could take spectra, which have so much more information content. And I'll touch upon that in the end. So the spectra allow us to see the motion along our line of sight, which is the one dimension that we're missing from the images. The images gives us the motion in the plane of the sky. Okay, so this is the model of what we see. So those stars we've been watching for the last 20 years. And over time, the case for the black hole has become increasingly strong. You can see my favorite star. Its name is SO2. It goes around every 16 years, and we can measure it not only in images. So things are in images when it's trailed by a dotted line, and it's measured spectroscopically when the line becomes solid. So it's the only star that has a complete orbit, both in the images and the spectroscopic domain. Okay, so why do we love SO2 so much? It's because it tells us what mass is inside its orbit. And to give you some context for what it's told us, let me just start off by saying, before we started this work, we knew that there was roughly 4 million times the mass of the sun in the region that's enclosed by this circle. And you can see that there's a lot of stars there. It turns out there's a lot of dust there. And at the time, you could not claim that there was a black hole simply because that region was so enormous. And now these orbits, in particular the orbit of SO2, which goes around every 16 years, tells us that there's 4 million times the mass of the sun inside a size that corresponds to the size of our solar system. So think about it. In our solar system, we have one sun. And in this region of space, same size, we have mass that corresponds to 4 million times the mass of the sun. And that is what has provided us with the strongest evidence today for the existence of supermassive black holes, not only at the center of our own galaxy, but actually anywhere in the universe. Okay, so ta-da. So you might ask, what are we doing now? Have we moved on? And the answer is absolutely not. There is so much more to do because we really would like to get a better understanding of supermassive black holes. We'd like to understand the physics of black holes, and we'd like to understand the astrophysics of black holes. So let me start with the astrophysics. The astrophysics is that today, well, actually, let me back up for a second. When we first started to announce the result of this work, the question about the relationship between black holes and the host galaxy used to be framed as which came first. It was like a chicken or an egg question. Was it the black hole or was it the galaxy? And we had all sorts of answers at that time. This was only 10 years ago, roughly, 10 to 20 years ago. But it became quickly apparent, not only the work that's done at the center of the galaxy, but in other galaxies, that the mass of the black hole seems to correlate very well with the mass of the central part of the galaxy, what's known as the bulge. And that's an enormous size difference, scale difference, and so big that you realize that the chicken or the egg question is just not the right question, that whatever formed the galaxy had to form the black hole, vice versa, and that there was some feedback that keeps the two in sync over the evolution of both objects. Okay, so that's the correlation. And our galaxy is an amazing place to study this because it's actually the only galaxy in the universe in which we can measure the orbits of stars. So we have a really unique laboratory for looking at the possible feedback. Now, I have to say, this is the other part of this work that I love, which is while we set out to answer a very specific question, what we found at the center of the galaxy has actually shown us that there are new questions that we didn't think or realize that we should be asking. So in fact, almost every prediction that could be made about what we should see around the black hole has been inconsistent with observations. So this is the brilliance of new ways of looking at things, having technologies that give you really just a fundamentally new way of seeing things that you've been thinking about for some time. So let me just give you a brief little tour of some of the things that we've been finding. I'm going to begin with a description of what we would expect in terms of the population of stars around the black hole. And astronomers like to, well, actually, for the point of view of this lecture, I'm just going to group stars into two classes, either young stars or old stars. So the bad joke you can make is it's just like in LA. You're either old or young, nothing in between. Okay, so we had some predictions, and you can tell whether or not a star is old or young by looking at the spectra. So the lore in astronomy is that you should only show pictures, but that's kind of unfortunate because there's such value in spectroscopy. So this is two stars, and it's the light that comes from these two stars, and you break it up into the rainbow of light that comes from each star. And you can see that there are what's known as absorption lines, and those absorption lines give us insight into the properties of the atoms that are in the atmosphere, and in particular, the temperature. So you can tell the temperature, and once you know the temperature and the brightness, you can infer a few things, and in particular, the age of the stars. This is a star that's roughly 1 million years old on the bottom and 1 billion years old on the top. So let's look at the predictions. So the stars, the prediction was that these old stars have had a lot of time, they're old, to interact with one another, and there should be a little entourage of old stars surrounding the supermassive black hole. So the prediction is lots of old stars. Now let's look at the prediction for the young stars. The young stars, well, young stars form out of big balls of gas and dust. These are enormous and they're fragile, fragile entities. Now, if you have such a thing near a black hole, this is not good news, because black holes have what's known as tidal forces. So if you were to put a young star, and these are two young stars I'm particularly fond of, they're a little older these days, but if you had them nearby, the black hole would pull much more strongly on the near side than the far side, and these objects would become what's known as spaghettified. So in other words, this is not where you want your children, and it's not a good place to form stars. The prediction was that there should be no young stars. Now this animation shows, this is a three-dimensional animation, which has a tremendous amount of information content in it, but I want to draw your attention to the colors of the stars. So we've coded the young stars as blue-green. We've coded the old stars as orange, and we've coded a new class of objects that we don't know what they are as magenta. So those were the things that we didn't even think to make predictions on. But you can already see that the things that we had predictions for, the old stars that were supposed to be plentiful, we see very few. The young stars weren't supposed to be there. We see lots of them. And so what's going on? And it turns out the ability to measure orbits of stars has provided us with very, very important insight. So hopefully, as you can see in this animation, as it pulls back, you can see that many of them were lined up in a common plane. And that provides us with an important hint that perhaps when these stars were being formed, there was a disk of gas and dust that surrounded the black hole that we don't see today, that could have formed those young stars. So this is very much akin to how planets form. There was a disk of gas and dust around the sun. You form the planets. It's also true that this picture suggests that our galaxy was perhaps much more active in its youth. In other words, that our galaxy, the black hole, had much more matter nearby to drive activity that looks somewhat akin to the active galactic nuclei that we were talking about in the beginning. Now, the last group is the one that I find most entertaining these days, the magenta stars, the ones that we didn't expect. And these objects are really exciting. This is actually these magenta objects are objects where there's clear evidence that the object is being torn apart at the surface. So there's no doubt about it. This is the first time an object that's what's known as tidally interacting with the black hole has been observed. And there's been a tremendous debate about what kind of object this is. Early ideas suggested that it was maybe a gas cloud that would feed the black hole, and we would get to see the black hole in a state of fireworks over the course of our lifetime. Turns out that has not held up. And our current thinking is that these stars are two stars, are pairs of stars that are close enough that they've had a three-body interaction with the black hole, such that the black hole has driven them to merge, making them incredibly large enough that they can experience these tidal interactions. So this is an exciting new possibility, but it really gives the sense that we're seeing phenomena that we didn't expect at the center of the galaxy. Now, where do we go from here on this front? One of the things I want to point out is that while we see a lot of stars at the center of the galaxy, we're only seeing the tip of the iceberg. We're only seeing the brightest stars. A typical star, in particular a star like our sun, is really quite far away from being detected at the center of the galaxy. So it's really important, or we're really driven, to want to improve our technology further to really understand what we see at the center of the galaxy. So while we see the things that we don't expect, I think it's important to keep in mind that we're only seeing the brightest objects. An analogy that I like to make today is it would be like trying to understand the financial market, but only being able to see the biggest transactions and being blind to all the little transactions that actually occur. You would have a really incomplete picture of what's going on. So it's really important as we go forward to see the typical star, and that understanding is important to our understanding of how black holes merge, when the two galaxies merge, and how gravity waves might come from the center of the galaxy. Another angle that we're interested in from the perspective of continuing on forward with better measurements is that these stars that are so close to the center of the galaxy allow us to test Einstein's theory of general relativity in a regime that's never been tested before in the near field of a supermassive black hole. So as SO2 goes through its next closest approach, which is in 2018, this is actually our first opportunity to enter the game of tests of general relativity. And then in the subsequent years, there's a whole series of different tests that can occur. So for this reason, I think it's probably obvious what I'm going to tell you next. I want better technology. So today, our technology is we use one laser to correct for the distorting effects of the Earth's atmosphere. It turns out that at 2 microns, where we do all our work, that only does half the job. And as you go to shorter wavelengths, it does even less. And if you were to go to a larger telescope, it would do even less. So what do we want to do? Today, we want to figure out how to launch multiple lasers. So this would be equivalent to doing, this would be what's called laser tomography. It's like doing a CAT scan on the atmosphere, and it would allow us to make the corrections that we can't make today. And if people are interested in learning more, I'd be happy to describe it. This would be allow us to do more science today with the current class of telescopes that we have in operation. And in the future, it's essential as we are beginning construction on the next generation of telescopes. So in the world, there are 3 major projects taking the next leap out to the class of the 30-meter telescopes. The one I'm showing you here is called the 30-meter telescope. It's a collaboration between the University of California, Caltech, Canada, Japan, China, and India. It's a big collaboration because it's an expensive project. It's a $1 billion project. That's a lot of money, but if you think about space, the next telescope after Hubble is the James Webb Space Telescope, and that's a $10 billion project. So this is a bargain in comparison. In Europe, there's the European Extremely Large Telescope, and then there's also the Giant Magellan Telescope. So there are 3 such projects going forward, and all of them assume that we have this much more advanced adaptive optics in operation. So I think that's an essential thing to be working on today's telescope. As we move forward, we think we will see something that's quite different. So this animation, again, shows a very small piece on the heart of the galaxy. It goes from no adaptive optics to where we are today to where we hope, or what we might see with the 30-meter telescope. Of course, we know so little about that population. That's just a guess. So in conclusion, let me just say this work has been done in collaboration with many, many, many people. And in fact, it's one of the, I think, the secrets to our success at UCLA is that there is a host of people who are interested in infrared astronomy. So I have certainly not done this work alone. In particular, I'd like to, I'd like Mark Morris, who's in the audience, to stand because he's my collaborator from the last 22 years. So this work would not have been done without him. So we want to thank him. I also want to give recognition to Arthur Levine and his wife Lauren and his son Zachary, who should also stand because they have enabled a tremendous amount of work at UCLA that couldn't have been done otherwise. And I've had both senior colleagues that I've collaborated more recently with over the last 10 years, and 22 years of amazing students and postdocs. That's the line that you can't see under all that text. So let me conclude that if nothing else, I hope that I've convinced you that supermassive black holes exist and that we are in the very fortunate position to have one in our very own backyard. I have to reassure you that there is nothing to fear. The sun will happily orbit with no danger, but it has provided us with a really wonderful laboratory for understanding both the physics and astrophysics of black holes. Thank you.
So, Andrea, that was just fantastic, stunning lecture, and I'm sure there are lots of questions. We've got about 15 minutes for questions before the end. So we've got a couple of roving mics, one on either side. So if you could put your hand up, you can make the questions succinct, that would help, and then we've got more time for more questions. Yes, there in the middle. And there's another one at the back there.
Yes, thank you very much for a wonderful lecture. What I wanted to ask you was, how will the results from the James Webb telescope compare with the results obtainable from the new generation of telescopes you just referred to?
So the James Webb's telescope is a 6-meter telescope, and this is a 30-meter telescope. So it's the same for this particular case where the issue is the crowding of the stars. You still get that diameter to the 4th power advantage. So for the heart of the galaxy, the ground-based telescopes will be much more powerful. Now, where the space-based telescopes offer a real advantage is the really large-scale picture. So in our work, we certainly already use the Hubble Space Telescope to get the larger scale picture where the crowding isn't such a dramatic problem.
Yes.
You asked for, you've told us about the adaptive optic approach. Is there any interferometric approaches to studying this particular black hole?
Yes, so there are interferometric approaches. So interferometry is the technique of combining the light from many different telescopes. So that's a technique that has been very successfully applied at radio wavelengths. And the reason it was so successful there to begin with, as opposed to the optical or the infrared, is this business of the atmosphere. So the atmosphere, what's known as the coherence length, the spatial scale over which there's no significant distortion, scales as the wavelength. In fact, the wavelength to the 1.2 power. So the longer your wavelength, the larger your coherence length. And it's fantastic if it were as large as your telescope. So at radio wavelengths, that coherence length is the size of the telescope. So you can easily combine the light from 2 different telescopes without worrying about the distorting effects of the Earth's atmosphere. So radio has successfully done this for a long time. And in terms of this particular black hole, the hope there is to build something known as the Event Horizon Telescope. And the objective there is to measure what's known as the shadow of the black hole. So at radio wavelengths, you see light from different phenomena. So rather than being dominated by the stars, you're actually dominated by light from the accretion flow. So the hope here is to see the accretion flow and to see how light bends around the Schwarzschild Radius, so the event horizon. So that's an important test, and that's should come online in roughly a year or two. So there are the early experiments that are being done. So that's a very exciting project. And then there's progress that's been made at applying this to infrared wavelengths, but it's much harder because you have to, if you're going to use the large telescopes, which you want to do if you want to have sensitivity, enough depth to see the stars that are as faint, and that's what you have at the center of the galaxy, these stars that are orbiting very close by. So you need to have adaptive optics working on each telescope before you combine the light. So this is technologically extremely challenging. But it is the underpinnings of a project that's known as Gravity that is happening on the Very Large Telescope, the VLT. The hope is to combine the light from the 4 8-meter class telescopes to look at the region very close to the black hole. And there you should see both the accretion flow and the starlight. The challenge for this technique is that your field of view is incredibly small. So it's the size of the smallest structures that we saw in the images before. So you're really getting a very zoomed in picture. And for both interferometric cases, you're getting a very, very small field of view. So brilliant, brilliant projects and allow you to probe very close to the black hole.
More questions? Yes, there's one here. Actually, there's 2 over here.
So what do you think a black hole is made of?
I don't know. I know. It's space and time. I mean, in some sense, we can't talk of what is it made of. I mean, it's how do we describe space and time that the black hole represents. So in a sense, you can realize that when gravity is so strong, nothing holds itself together to be able to describe what it's made of. So the real challenge actually is describing the nature of space and time. There is stuff, yes.
Stuff.
Yes. Stuff in its purest form.
Okay, we had another question just here, I think. Yeah. And then there's another one down here on the left we want to go.
What's the velocity of the objects going around the black hole?
What's the velocity of?
What's the velocity of the objects going around the black hole?
So the ones that we're seeing in this work, at closest approach, they're roughly 10,000 kilometers per second. So roughly 1% or so of the speed of light.
Question here at the front. Yeah.
You've described ordinary black holes with solar masses of 30 to 100, and then you described supermassive ones, which are 4 million solar masses or something. Have you observed any intermediate masses, or do you think they exist?
So this is a great question. So we have, on the one hand, what we call the ordinary mass black holes. Those are the 10 times the mass of the sun or so. And then we have the supermassive black holes, which are 1 million to 1 billion. So what about the whole scale in between? So they are the elusive intermediate mass black holes. And there have been claims of intermediate mass black holes at the heart of globular clusters. So these are clusters of stars in our galaxy. But there's tremendous controversy that still surrounds whether or not those objects exist.
There's a question just here. Yeah. No.
How easy or possible is it to generalize from all of the things you learn about our black hole and our galaxy to potential other ones? Is there anything we can kind of compare it to know whether it's an outlier or representative?
Well, in terms of the behavior that surrounds it, it's interesting. So one of the closest examples of a supermassive black hole where we can begin to get this kind of detail is a galaxy known as M31. And there's now evidence that around M31 there are young stars. So it's starting to look like there are other examples where the environment around the supermassive black hole may have a lot of similarities to our own. But we are certainly in a situation where we can learn so much more about the environment around our galaxy's center than any other one. Maybe the analogy is what we can learn about the sun compared to typical stars. So we do like to extrapolate, and there's nothing that seems to make our galaxy look special, so we happily extrapolate away.
Yep. Another one here at the front.
Actually, let me follow up. I mean, this is also one of the things that, future telescopes should help us. So with future telescopes, we will be able to start to get more detail to ask that question, which is how, is our galaxy an outlier or is it a typical galaxy?
Yeah. Is there an upper limit to how big supermassive black holes can get?
Is there an upper limit? Well, there's an upper limit to what's been observed. So that I think the most massive supermassive black hole is, I believe, 10 billion times the mass of the sun.
We're looking for diversity in age and background and everything here. So feel free to ask a question, and it's an opportunity for you, so don't feel held back anyway. Yeah.
Is there an end to a black hole?
An end, you mean end in terms of its evolution,
Yeah.
or?
Yes, as is evolution.
So black holes, can they evolve or can they change in any way? And the only hope for a black hole to evolve that we know of is what's known as Hawking radiation. But it's a very small amount of radiation for this supermassive black hole. So in other words, it's quite a quite small effect. Nonetheless, there's if you're really interested in this question, there's a wonderful book written by Fred Adams called The Dark Ages, where he evolves the universe to its ultimate end. And you do get a universe full of lurking black holes. Supermassive black holes, because those are the ones that sort of survive for the longest time. Yeah.
Okay, we've got lots of hands here at the front. Am I missing people at the back? Maybe there's somebody over there at the back. Yeah. So one at the front here first, yeah.
Well, this is probably a really stupid question, but what is a black hole a hole into?
No, it's not a stupid question because we don't know. we don't, inside the event horizon, we can't get any information inside that point. So at that point, we can hypothesize about possibly black holes connecting to white holes on the other side through a wormhole, and possibly connecting different parts of a multidimensional universe. So those are theories, but today it's beyond the reach of experimentation. Yeah.
Yeah, the back.
You were talking about the dust particles that were protecting the young stars. Do we know when that may have disappeared, and have you seen that anywhere else in any other galaxies? Because is that something that may have disappeared into the black hole, or?
So this is the disk of gas and dust that gave rise. It is the idea that there was a disk of gas and dust actually comes from observations of active galactic nuclei. So we think that what's feeding that tremendous amount of energy is a disk, a gaseous disk. So we think that in our galaxy that disk survived for the time scale it takes for those stars to have formed, and then it probably depleted it. And in fact, Mark Morris has this wonderful picture of what happens at the center of the galaxy as a cycling of activity, so that the galaxy may go through periods of intense accretion onto the black hole and star formation, and then subside as those stars blow off or blow out the gas that is the building blocks of the stars and the stuff that's accreted. You should talk to him after the lecture.
Okay, there's one here at the front. Let's go here. Gentleman in white.
Yeah, I was just curious to know where we look in the night sky to not see our very own black hole.
Okay, so in the summer, there's the constellation of Sagittarius, which is the teapot. And the teapot pours into the center of the galaxy. So that's the device you can use to find the center of the galaxy.
And how did you locate that center?
Oh, right. How did we know where to point, or how did I know where to put that box? There are two clues. One is that the density of stars we expect to increase towards the center of the galaxy. So in fact, at the center of the galaxy, if you discount what's old and young and just count the number of stars, there is a peak that you can localize. And so in fact, that was the recognition that there were stars that you could detect in the infrared was the work done in the 60s by my colleague Eric Beckland. So that's one clue of where to look. And the other clue is that at radio wavelengths, there is a radio source that's not very strong, but it has emission that doesn't look like starlight and kind of looks like a mini active galactic nuclei. So it was one of the things that Donna Lyndon Bell and Martin Rees were asking is that unusual radio source, which we fondly call Sagittarius A star. It's an awful name, actually. This is where people tried to be too clever. So Sagittarius for the constellation of Sagittarius. A because it was the brightest radio source in the region. And it wasn't really star, it's asterisks. After the nuclear physicist who used the asterisk to say excited state. So it's really, they were trying to say Sag A, not a star, by the asterisk, but we all say Sagittarius A star. Anyway, so there was a radio source that had unusual characteristics, and you can pinpoint that fairly accurately. And that happens to reside roughly where the star density is peaking. So we had a general idea, or good enough idea of where to point our big field of view, and then we could more accurately locate it. And the orbits of stars, of course, tell you exactly where the black hole is.
Questions? Yeah, there's a flood of them here, and there's somebody over there on the right. over there.
If nothing escapes from a black hole, not even light, then how does gravity escape and have an effect on the surroundings?
That's a good question. So I think this is where we get into a little trouble with our classical description of not classical objects. So my relativity friends would cringe probably when I was saying mass confined to zero volume, because what we are talking about is the curvature of space-time. So we can talk about light traveling through the curvature of space-time, but when we talk about gravity, we're really talking about the structure of space-time. So that's how we get out of what you're asking. So the problem is that we've used a classical device to describe physics that's not classical. That's my out. Sticking by it.
One question.
Yeah.
Hello. Hi there. I was recently watching a program where it described I think this year with the gas cloud or something like gas cloud, I think you described it as something different was going to go past and you would see matter being sucked into the black cloud, the black hole. What are you actually going to expect? Because it looked like you were saying that it might actually be something different and not what I had seen in this program.
Yes. Well, it turns out there are two groups that have been doing this kind of work for 20 years. So like in most science, there's usually a good bit of healthy competition. So there's the group at UCLA, and there's a group in Germany headed by Reinhard Genzel, who uses the Very Large Telescope. So they have had a very different idea of what these magenta objects are, and that was the original claim, was that it was a gas cloud. And the nice thing from our perspective is that it's testable. So we were pretty sure that it wasn't a gas cloud. There's a very simple explanation for why we were so cynical or skeptical about this. The gas cloud is actually one of the hardest observations that we've ever made spectroscopically. In other words, it was only possible when adaptive optics came online. And so this gas cloud hypothesis required that the gas cloud formed the minute adaptive optics came online. And it had been seen for the 10 years that adaptive optics was online, and then it was going to be disrupted the year after the paper was published. And in astronomy, anytime you say that you're observing at a special moment, you're just usually wrong. Because we're not usually that lucky. So you then have to ask, well, what could give rise to such a phenomena? In other words, you're seeing the problem is that to get those tidal interactions to happen, the object has to be 100 times bigger than the typical star that we're seeing, either the young star or the old stars. It's 100 times bigger. So a typical star won't do the trick. So a gas cloud would definitely do the trick. It's just that a gas cloud doesn't survive in this region very easily. That was the whole problem with the young star hypothesis. So you have to say, well, it just recently formed, and then when it makes its first closest approach, it's going to completely fall apart. So it turns out that most stars start their lives out as binary stars, if you look at other parts of the galaxy. And so then if you ask, well, what's going to happen to a close binary star in relationship to the black hole, you get this three-body interaction where what's known as the eccentricity of the orbit gets pumped up and exchanged for the relative orientation. So you basically get an oscillation between the shape of the orbit and the orientation of the little binary compared to the thing going all the way around. And if you pump up the eccentricity high enough, you can get them to merge. And when the two stars merge, what happens is that those stars go back to looking like an incredibly young star, which happens to be 100 times bigger than a typical star. So it has actually the characteristics that are required without having to invoke anything particularly extraordinary, except for the fact that no one had been talking about binary stars at the center of the galaxy. But most of these stars are massive stars. Massive stars are almost 100%. They're 80% binary stars that are quite close. So we're doing a lot of work now that is focused on, can we find the signatures of binaries before they merge? And now we're actually starting to find many, many other examples of these The original one was called G2. So we're calling them G2-like objects, G2 and friends. And it looks like there's quite a few of them. And in simulations of the binary stars that I'm doing with a colleague at UCLA, Professor Smadar knows, it looks like it's completely reasonable to invoke this binary star scenario to explain what we're seeing here. Now, the idea that that gas cloud was going to feed the black hole was interesting, but the gas cloud could only be 3 times the mass of the Earth. That was also not much gas. What's exciting about this idea is that the brightness of these stars suggests that they're 2 times the mass of the sun. That's a lot more mass. And when they merge, there's plenty of stuff that just comes off of it. So there, in fact, may be far more material that's available to fall down onto the black hole. It's just not as clean a process, I think, as was originally depicted, because you're losing that mass and you're losing it into a stream of existing gas out at a distance the size of the solar system. So it's an interesting story, but I think it's an evolving story.
We have to wrap it up there. We're running out of time, I'm afraid. But just in closing, I want to say the Bakerian Lecture and Medal is, of course, a great honor. It's a fantastic achievement, and it's wonderful that Andrea's won this prize. In previous years, we've given out the medal, the scroll, and a big fat check at the end of the lecture. Nowadays, we have a little prize-giving ceremony with some of the great and the good, which we did a few months ago. So it's somewhat different this year. But nonetheless, I think it's been an extremely special occasion because it's not just an award, it's a lecture, and this is one of the greatest lectures I've heard for a while. And so I'd like to thank Andrea not just for being a great scientist and bringing us brilliant science, but also doing a superb job at communicating with us. Thank you very much indeed.